Hey, this is Mr. Ray, and this is Unit 6. Still, it's integration and accumulation of change. We're going to be doing the fundamental theorem of calculus. Yes, the first three letters is fun. And you're like, no, the last six letters are mental. So, yeah, it's fundamental. It's fun, and it also will make you a little bit mental. So let's take a look at the fundamental theorem of calculus. What the fundamental theorem of calculus says is that if a function f is continuous on the closed interval of a to b, and f, capital F, is the indefinite integral of f on a to b, then you can see the integral of f of x, the function with respect to x, from a to b is equal to this capital F of b minus capital F of a. And what this is doing is this is kind of connecting our differential calculus with our integral calculus. It's connecting everything together. And so as an example, this tells us about what's called a definite integral. Okay, we've been doing, up till now, we've been doing Riemann sums. We've been doing indefinite integrals, which is just what is the integral of something. But now we're going to be taking a look at what's called a definite integral. So let's say we're going from 1 to 3. And let's say we have x squared plus 2x plus 3. And we're going to do our integral here. So what's the integral of this x squared is going to be 1/3 x cubed plus x squared plus 3x. And we're going to take a look from 1 to 3, which means these are kind of our bounds of what we're finding the area underneath. And so what do I have? I have 1/3 3 to the cubic power plus 3 squared plus 3 times 3. I'm plugging in that value for 3. And then I'm subtracting 1/3 1 to the cubic power plus 1 squared plus 3 times 1. And so I'm doing the upper bound minus the lower bound. So I have 1/3 times 3 cubed plus 3 squared plus 3 times 3. And I end up getting 27 minus, you can see I have 1/3 plus 1 plus 3, and I have 4.33333. Okay, so 27 minus that answer is going to give me 22.67, and that would be the area under this function's curve from 1 to 3. And so that is the area underneath that. And so that is what's called the first fundamental theorem of calculus. The second fundamental theorem of calculus is often sometimes called the first fundamental theorem of calculus. It kind of takes everything together, and we got to understand this a little bit deeper. This is a little bit more complex, but I think we'll understand it if we go step by step. So this says if function f is continuous on an open interval I and a is any point in I, then f is defined as, you can see this function right here. So let me kind of give you an example of what's going on here. So let's say we have this. We have a function right here, and this function is y equals f of t. We're going to call it lowercase f of t. And we have a right here, my lower bound, and we have b, my upper bound right here. And let's say we have some value x in between this continuous function of a to b. And so this value x, which is obviously f of x, what this is telling us, it's telling us the area under the curve from a to x. The area under the curve from a to x. And you can see what's happening here is this f of x, this capital F of x, is the area. This is the area under the curve from a to x of f of t dt. Okay, of f of t dt. And this is where this x value is inside my it's inside my interval of a to b. Okay, and so if we take a look at the genius of the fundamental theorem of calculus, what I'm going to show you is this, let's take the derivative of this side over here. So I'm going to take the derivative of capital F with respect to x, which means I'm also going to take the derivative with respect to x of a to x of f of t dt. And when I take the derivative of this integral, I end up getting f of x, which means that every continuous function f has an antiderivative called capital F, which was the first fundamental theorem of calculus. And this connects our differential calculus with our integral calculus. So let me give you a nice example here. Let's say we have d of dx. We're taking the derivative of the integral of cosine of t over natural log of t dt. So here's where the second fundamental theorem of calculus is put into play. We're taking the derivative of this integral with respect to t of cosine of t over natural log of t from pi all the way to x. And so sometimes you'll see this on an AP Calculus. You will definitely see this on an AP Calculus exam. And you see all this mess, the derivative, the integral, they kind of cancel out. And what's left is cosine of x over natural log of x. You're literally just putting x in for t right here. And so that is what is happening in this the second fundamental theorem of calculus. Now, let's say we have x squared. Not just x squared. So we have cosine of x squared over natural log of x squared times the derivative of x squared, which is 2x, because the chain rule applies. The chain rule still applies, doesn't it? Which means, do you see how when we just had x, we're really multiplying by 1, aren't we? So let's take a look at how the fundamental theorem of calculus comes into play. So it says this: the graph of the function g is shown right here, and we're taking a look at f, which is the area of g of t d of t, and we're going from -3 all the way to x, and we're evaluating the area where x is equal to 1. So we're going from -3 all the way over here, all the way to 1 all the way over here. And so we're taking a look at what is the area underneath. So take a look. I'm going to take a look at the area. I'm going to split it up into nice sections. You can see this area of this big rectangle is 1, 2, 3, 4. 4 times 2 is 8. That's 8 units high. This one is 1/2 base times height because it's a triangle, so 1 times 1 is 1. And 1/2 of base times height, we have 1 times 1, 2, 3, that is 3. You add all of this up and you get an area of 12, an area of 12 units. And that is because we use the first fundamental theorem of calculus. Now, I hope you can see we just evaluated f of 1 here, of f of 1. Let's say this is what it says. Another example is g of x equals the integral from 2 to some value x of 10t plus 2 d of t. And we're looking at g prime of 3. So what is g prime of x equal to? Of what's the derivative of this integral? What's the derivative with respect to x of the integral of 10t plus 2 dt? The derivative of the integral is 10x plus 2, isn't it? This is the second fundamental theorem of calculus. And so we just plug the x in for the t. And what's the derivative of x is 1. So we're multiplying by 1 ultimately. Which means what's g prime of 3 would be 10 times 3 plus 2, which is 32 for that second fundamental theorem of calculus. Let's do one more example here. Here we have big f of x is equal to the integral from -2 to sine of x of 3 of t dt. And we want to know what f prime of x is. So we're taking the derivative with respect to x of -2 sine of x 3t dt. Okay, so we're taking the derivative. So we're going to plug the sine of x in for where t is. So 3 times sine of x. But don't forget we also have the chain rule. So what's the derivative of this value up here? What's the derivative of sine of x? Is cosine of x. And that is your second fundamental theorem of calculus. I hope this made sense. You can go back and rewatch the video again. I think it'll make more sense the second time, and even the third time, and even the fourth time, and it'll make me some money on YouTube as well. So hope this made sense, and I hope it was a little fun. Fundamental. See you guys.